So here we have the electromagnetic spectrum, going from low energy up to high energy. And what we're putting on this number line here is the wavelength in meters. So here, 10 to the fifth, that's 100,000 meters long. It's a really long wavelength, right? And down to 10 to the minus 15th wavelength, which is crazy, crazy small. And here we have just kind of a drawing of longer wavelengths here and shorter wavelengths, and these look like they have more energy, and they do. Short wavelength, high energy. So along here, we have radio waves. These are low energy, they have long wavelengths, and that's why they can travel great distances. In here are the microwaves, and those are the same microwaves that heat your food in the microwave oven. Here we have infrared radiation, and when we get into this area here, about 10 to the minus 6 or so meters, this is the visible light. So this little tiny section here is the visible light, and then we go to ultraviolet radiation, which is what can give you a sunburn, invisible light from the sun. That's got more energy, and then X-rays have even more energy, and then gamma rays have the most energy. Because this is such a small section here in the total electromagnetic spectrum, but it's a part that we're very interested in because it's the light that we can see with our eyes, this is taken down here and spread out. Sometimes the way this is graphed is confusing. So we're spreading it out here. This is going from 750 nanometers up to 400 nanometers. So this is 400 times 10 to the minus 9 meters, and this is 750 times 10 to the minus 9. We use nanometers to express the wavelength of visible light because it's an appropriately sized unit. It gives us nice numbers, 400 to 750. So we see that red light has the least amount of energy and violet light has the most. And they always go in that order. So then your book talks a little bit about the different types of radiation. You should be familiar with these. Gamma rays, these are produced by the sun and the stars and also by some unstable nuclei present on Earth. X-rays will go through many solid substances. They have enough energy to do that. They don't go through like centimeters worth of lead or meters of concrete, but they will go through like your skin so they can take pictures of your bones. So X-rays are used for imaging. They can also be used for destroying tumors. And this is kind of interesting. So the more energetic electromagnetic radiation, X-rays and gamma rays, can be used to destroy a tumor. So if this is the tumor and here's the healthy tissue around it, sometimes the tumor is in a place like in the middle of your brain where they can't just cut you open and take the tumor out because that would destroy some other things that are pretty important, like your brain, right? So then what could they do? Well, there's a technique called gamma knife, and what they do is they take radiation from multiple directions and target all of it on the tumor. So there is some damage along here, and some damage here, and some damage here, but not very much to the healthy tissue around the tumor, but it's all focused on the tumor, and so the tumor gets a lot of radiation, and they can use that to destroy a tumor that's located where they can't operate. So that's pretty cool. Ultraviolet rays, ultraviolet light, that's the part that gives you a suntan and or a sunburn. It's still damaging to biological molecules. Visible light is not harmful to biological molecules. It's lower in energy. It doesn't have enough energy to damage tissue. Have you ever wondered about vision? What exactly is vision? How do we see stuff? Did you ever think about that? Well, yeah, you've got rods and cones in your eyes, right? So this light, the visible light, is of a frequency and an energy such that when it hits the rods and the cones in your eyes, it causes those molecules to rearrange. It has just the right amount of energy to cause them to rearrange. And that rearrangement signals your brain, and your brain interprets that as vision. It's really pretty mind-boggling when you think about that. Then there's infrared light. This is not light that you can see, but it is that heat that radiates off of a warm object. So like in lab, when I warned you about the crucibles, I said, put your hand near the hot crucible, and if you feel heat, don't touch it yet, right? That's infrared radiation that's coming off. Any hot body will give off infrared radiation. And that infrared energy can be used in night vision technology. So here we have two pictures. Here's a guy with his dogs, right? Normal photograph. Here's the same picture taken with an infrared technology camera. And so we're not seeing visible light now, we're seeing the infrared light. And the infrared light is over a range, and so you have different energies. And so we see the warmest places as being red. So we see the exposed skin on the guy's knee and his face, and here's the face of the dog, and the eyes and the ears and the mouth. And the darker places are cooler. So there you have it, proof that dogs' noses are cold. See, his nose is darker. So it's not actual vision in the night, but it's using the infrared radiation that comes off of warm objects. You have to have some sort of a sensor, or basically a computer, to interpret it and make it into an image that you can then see with your eyes. But this is really useful for finding people who are hiding in the woods, right? You may not be able to see them because it's dark or because there's foliage, but the infrared radiation is there and can still be detected. Microwaves. The basic principle of the microwave oven is that the microwaves are very efficiently absorbed by water molecules. And so the microwave will work well on foods that have water in them. If you put something very, very dry in there, it's not going to work very well. And then radio waves. So your cell phone signal, TV signals, AM and FM radio, all of that, radio waves. Okay, let's go back, because I kind of forgot something maybe. Way back, okay. So one thing you should know is the order of the visible light here. It's always in the same order, and you can remember that. Roy G. Biv. Aren't you glad that's not your name? Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. So red, orange, yellow, green, blue, indigo, violet. That's the order of the colors. Now the tricky part is, how do you remember which end is higher energy? Well, what's going to give you a sunburn? High energy or low energy? High energy. What part of the sunlight burns you? Ultraviolet. So the UV lights that give you a sunburn are just on the other side of the violet light that we can see. This is the high energy side, and that's the low energy side. That's how I remember that. Okay, let's see if I can get back to where we're supposed to be. Okay. So this asks us to arrange the colors of visible light, green, red, and blue, just 3 of them, in order of increasing wavelength, increasing frequency, and increasing energy per photon. So let's see if we can figure this out without looking at that table, that graph. Okay, so I think that the energy is easiest to remember. It goes in order, Roy G. Biv. And then I remember that violet is right next to ultraviolet, ultra meaning more. And so this is the high energy end of the visible spectrum, and this is the low energy. So when it asks for increasing energy, that means I want to put the low energy one first, and then the one that's in between, and then the highest energy one last. So which is the lowest of green, red, and blue? Red. So I'm going to say red is lower in energy than green, which is lower in energy than blue. That's an ugly G, but I don't care today. It looks a lot like my other ugly G. Then frequency and wavelength. Well, frequency, we drew those pictures, right, of something with short wavelength, and we said that was going to have a high frequency, high energy. Okay, so at this end, the high energy is the one that looks like it's jumping all over the place, right? And the low energy is the one that looks slow. So which one has higher frequency, that one or this one? This one over here, right? If this is passing you at the same rate of speed as this one, this is going to hit you more times. So the energy goes RGB. Frequency, this is going to be high frequency. High frequency corresponds to high energy, and so the order is the same. Red is low frequency, green is in the middle, and blue is higher frequency. Any questions? What about wavelength? Backwards. So we drew these little pictures to help ourselves. We can look at this. Well, this is a long wavelength. The distance between one peak and the next is longer here than it is over here. So this is short wavelength. This is long wavelength. That's the opposite of the energy and the frequency. So we're just going to turn these around, put blue first, and then green, and then red. There will be questions like this on the exam that ask you to order things by increasing or decreasing. And I always get a number of students who get it wrong because they don't understand how to answer the question. They know the material, but the question itself confuses them. So order of increasing means that you put the smallest one first, and then the next largest and the next largest up to the largest one. Okay? If it was decreasing, you do it the opposite. Start with the biggest and go to the smallest. Okay? I guess they never gave you questions like that on all those standardized exams they made you take. That would have been useful. Any questions about this?